We know that if we have a triangle and we take the orthocenter of the triangle and connect it like this, like this, like this, and like this, then this angle will equal this angle. Well, it turns out that this point doesn't necessarily have to be the orthocenter for this angle to be equal to this angle. It could just be a random point on this altitude of the triangle. And this statement is called Blanchet's theorem. See, here I took a random point on this altitude, I connected it like this and like this to get this point and this point, and then connected these 2 points with this foot of the altitude like that and like that. And that's how I got this angle and this angle. And now I'm going to prove they are equal. For this, I just need to prove that the 4 points marked in green are in harmonic division. Because if that's the case, then I have 4 points in harmonic division, and I have a right angle here, from which it follows that this line is the angle bisector of this angle, and that this line is the external angle bisector of the same angle. Now I'm going to project these 4 points with respect to this point to this line. This point would stay in its place, this point would go here, this point would go here, and this point would go here. Then I need to prove that these 4 points are in harmonic division. But now take a look at this triangle. We have that this point is chosen inside of the triangle, and then we connect like this, and like this, and like this, here, meaning that these 4 points are in harmonic division. From here, it follows that the 4 green points are in harmonic division, and from the 90 degrees angle here, it follows that this angle equals this angle, and furthermore, this angle equals this angle. This here is called the generalized Blanchet's theorem. Suppose you have a quadrilateral, and suppose this is the intersection point of its diagonals. We're going to intersect this line and this line at this point, and this line and this line at this point. Then drop a perpendicular from this point to this blue line. This red segment here would be a perpendicular. We have to prove that this small angle here equals this small angle here, and this angle equals this angle, from which it would of course follow that this angle equals this angle. Essentially, this means that the red line is not only the angle bisector of this angle, but it's also the angle bisector of this angle. And respectively, this blue line is the external angle bisector of both angles. In order to prove that the red line is the angle bisector of this angle here, we need to show that this point, this point, this point, and this point are in harmonic division, where this point is defined as the intersection of this line and this line. Because then we would have a right angle right here, and a harmonic division here, from which it would follow that this is the angle bisector of this angle. And now let's project this cross ratio onto this line with respect to this point. So this point would go here, this point would go here, this point would stay in its place, and this point would go here. Then it suffices to show that the 4 points marked in green are in harmonic ratio. But see, we have this triangle with this point on the inside, and then we connect like this, like this, like this, and like this. And therefore, these 4 points are in harmonic division, meaning that this is the angle bisector of this angle. What remains to be shown is that the red segment is actually an angle bisector of this angle here as well. But it suffices to prove that this point, this point, this point, and this point are in harmonic division because we have a right angle here. And if these are in harmonic division, then it would follow that this is the angle bisector of this angle. To prove that these points are in harmonic division, we're going to project them onto this line with respect to this point. Then this point would stay in its place, this point would go here, this point would go here, and this point would go here. So these 4 points would be the projection of these 4 points, meaning that the cross ratio is preserved. But we just saw that these 4 points are in harmonic division, and therefore these 4 points are in harmonic division, which means that this red line is also the angle bisector of this angle right here. This means that this angle equals this angle equals this angle, and this angle equals this angle. And that finishes the proof of the generalized Blanchet's theorem. This is the optional problem. We have a circumscribed quadrilateral, which means that there exists a circle that touches all of its 4 sides, and let this be the center of the circle. Let this line intersect this line at this point, and let this line intersect this line at this point. Then we can define this line here, and drop this red perpendicular line from this point to this line. That's how we define this point, and now we connect it with the 4 vertices of the quadrilateral. That's how we define these green angles. We need to prove that this angle equals this angle, that this angle equals this angle, and that this angle equals this angle. Or in other words, that the red segment is actually the angle bisector of this angle here, and the angle bisector of this angle here. And here's the solution. From the generalized Blanchet theorem, we know that if we take the 2 diagonals of the quadrilateral and we intersect them here, and then we drop the perpendicular from this point to this line, then this line would be the angle bisector of this angle, and also it will be the angle bisector of this angle. And so, if we just prove that the intersection of the diagonals lies on this red segment defined by the center of the circle and the foot of the perpendicular, then we would be done, because it would follow from the generalized Blanchet theorem that this angle equals this angle, this angle equals this angle, and this angle equals this angle. So now let's try to prove that this point, and this point lie on a straight line. Or in other words, let's prove that the line defined by this point and this point is perpendicular to this line here. Now let's take these 4 points of tangency of the incircle with the sides of the quadrilateral, and let's apply Briançon's theorem for the hexagon defined by this point, this point, this point, this point, this point, and this point. It's a degenerate hexagon because one of its angles here is 180 degrees, and another angle here is also 180 degrees. But it's a circumscribed hexagon because this circle essentially touches all of its sides. So Briançon's theorem tells us that this line, and this line intersect at one point, because these are the 3 diagonals of the hexagon. Similarly, we can apply Briançon's theorem for the hexagon defined by this point, this point, this point, this point, this point, and this point, which would give us that this line, and this line, which are the 3 main diagonals of the hexagon, intersect at one point. And therefore, we can define this point not as the intersection of this line and this line, but as the intersection of this line and this line. Now we need to prove that the line defined by the center of the circle, the intersection point of this line and this line, is perpendicular to this blue line. Now let's call this distance A and this distance B, and let's call this distance C and this distance D. We need to prove that this angle is 90 degrees, and so this is equivalent to proving that B squared plus D squared equals A squared plus C squared. Let's call this distance from this point to this point of tangency by x. Then we know that this distance is also x because this is also a tangent line to the circle. Let's call this distance y. For the same reason, we know that the distance between this tangency point and this point is also y. Let's label this distance as m, this n, this p, and this q. And now let's apply Stewart's theorem for this triangle and this point lying on this side. Then we get that b squared equals m times x squared plus n times x squared divided by m plus n minus m times n as given here. But now we have m plus n, which cancels out with this m plus n, so what's left is x squared minus mn, and that's the value of b squared. Now let's apply Stewart's theorem for this triangle and this point lying on this side. Then we have that a squared equals p times y squared plus q times y squared divided by p plus q minus p times q as given here. And in the same way, p plus q cancels out with p plus q, and we're left with y squared minus pq for the value of a squared. But the power of this point with respect to this circle is m times n, and it's also p times q, and therefore pq can be replaced by mn. So a squared equals y squared minus mn. Let r be the radius of the circle, so this is r and this is also r. And since this line is tangent to the circle and this line is tangent to the circle, we have a 90-degree angle here and here. So by applying Pythagorean theorems for this triangle and this triangle, we get that d squared equals y squared plus r squared, and c squared equals r squared plus x squared, as written here. And now we can replace b squared with x squared minus mn, a squared with y squared minus mn, d squared with y squared plus r squared, and c squared with x squared plus r squared in here. And then what we get is x squared minus mn plus y squared plus r squared, whether it equals y squared minus mn plus x squared plus r squared. But this equality obviously holds because y squared cancels out, r squared cancels out, x cancels out, and mn cancels out. And therefore, this equality here is true, meaning that this angle is 90 degrees as desired.